So the rational functions and asymptotes section starts out with defining what a rational function is. It's a polynomial divided by a polynomial. And remember, your polynomials, for example, have to have a whole number, a counting number power. And it can't have a fraction power, can't have a negative power. They've got to be counting numbers. So 0, 1, 2, 3 are good powers or exponents that you can have. And that's what's going to make up our rational functions. So for this section, it says assume P of x and Q of x have no factor in common. Here's why. If I take my y equals x minus 2 over x squared minus 4 and I factor this, the top doesn't factor, but the bottom is the difference of two squares. So notice the x minus 2 can cancel with the x minus 2, and I can reduce the fraction down to 1 over x plus 2. When I reduce the fraction down, the vertical asymptote is found by setting the denominator of the reduced fraction equal to 0, solve for x. But here's the thing, that thing that we canceled out, that factor that we canceled out, that's something as well. That x minus 2 equals 0, x equals 2, that's something that we can't use in our function either. I mean, think about it. If I plug in 2 right here for x, 2 squared is 4, 4 minus 4 is 0, we got problems there. So what happens at 2? Well, let me show you real quick here. Pull up your graphing calculator if you have one. And what I did was I typed into the y equals screen x minus 2 divided by x squared minus 4. So if I graph that, that's the actual picture of it. And you can see at x equals negative 2, there's a break in the graph right there. That's where my vertical asymptote's going to be. That's the x equals negative 2 that we found here. All right, but at x equals 2, and you have to look kind of hard for it, but at x equals 2, there's like a break in the graph. There's like a hole. And if you trace, and watch my x value here, like if I go to the left, 1.5, 1.6, 7, 8, 9, and then do 2, notice I don't have a y value there, and I don't have a blinky dot on my graph anymore. But if I go to the right, 2.1, 2.2, I end up with my blinky dot. So if you scroll back, something happened at 2. And that's where you have a hole. I mean, it's a physical hole. And it's also called a removable discontinuity. That's what we did. We removed the factor and we created that, we took that hole out of the graph. So if I graphed this function, I wouldn't see the hole. I would just see the vertical asymptote. So this hole, again, is called a removable discontinuity. Okay. So definition of an asymptote, it's like a guideline. Your graph is going to get really, really close to it. And on a vertical asymptote, it'll never cross it because you can't cross it. Otherwise, you're going to make your denominator equal to 0. So it's just going to ride along the vertical asymptote here. So on the left side of 3, the curve is going down to negative infinity. That's here. The left side of 3 would be on this side. So as we come into 3 on its left side, my graph is going to negative infinity. So the way we say left of 3 is 3 with a negative up there. And then on the right side of 3, so coming in on the right side of 3, coming in and approaching it, its graph is going up to positive infinity. So that's what all of this means. Y is going down, we're going to negative infinity as x approaches 3 from the left. And your y is blowing up to positive infinity as your x approaches 3 from the right. Okay. The domain and vertical asymptotes are closely related, and we saw that in some of our examples on the next page here. This was the part that the instructor went over in class with you. As x goes to negative infinity, you're approaching this horizontal asymptote here. All right, and the horizontal asymptote is at y equals 2. That's what your graph is approaching as you go to the far left when x goes to negative infinity. As you go to the far right, as x goes to positive infinity, your y values again approach the horizontal asymptote y equals 2. Okay. And then this one we did in class, again, finding the vertical and horizontal asymptotes. Right. So this is kind of where I picked up, find the vertical asymptote, set the denominator equal to 0, solve for x. It's got to be x equals, all right, some number for a vertical asymptote. You got to start out with x equals. Okay. And so we did a few of these. Example 3, though, is the one we skipped over. And again, we're only focusing really on the denominator here because, once again, you were told at the start that you're not going to have to worry about wholes. So you're not going to have to factor the numerator and see if something's going to cancel out. You're just going to factor the denominator only. So x to the 4th minus 1 equals 0. This is the difference of two squares. All right, and then set each factor equal to 0, solve for x. So x squared plus 1 equals 0, or x squared minus 1 equals 0. Solve for x. And then again, square root means you're putting in a plus or minus. So we have two vertical asymptotes, x equals positive 1, x equals negative 1. The other factor doesn't give you a vertical asymptote. When I subtract 1 and then take the square root of negative 1, that's an imaginary number. So this factor doesn't give us out a vertical asymptote, but we do have two right here. Okay. So again, vertical asymptote, set the denominator equal to 0. Now for the domain, it's set the denominator not equal to 0. So it's where you just solved, only it's going to be the not equals, plus or minus positive 1. So your domain would be negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. And then what happens here at negative 1 is your vertical asymptote. And what happens here at this break in your graph, x equals 1, again, vertical asymptote. Okay. We did the how do you find a horizontal asymptote, and that's all about looking at the degree of the numerator versus the degree of the denominator. And you have three cases that it's going to fall into. Either case A, where the numerator's higher than the denominator, then you have no horizontal asymptote. If the denominator is bigger, all right, the degree on the bottom is bigger, then it's going to be y equals 0, automatic. Your fractions go into 0. And if they're equal, the degree on top is equal to the degree on the bottom, then it's the, you're looking at the lead coefficient of the numerator divided by lead coefficient of the denominator. And those were the three examples that we did here. Right? The degree on top versus the degree on the bottom, that's why we have no horizontal asymptote. This fraction's blowing up. If the degrees are the same, then you look at the leading coefficient, take 8 divided by 2, but then make sure you're writing y equals. If it's a horizontal asymptote, you've got to make sure you're writing y equals and then some number. Okay. Then the last thing in this section is finding the intercepts. And this really isn't too hard. To find a y-intercept, you let x equal 0, solve for y. And this just involves arithmetic. So for these problems here, I'm going to go ahead and find the y-intercept. So y equals, plug in zeros for x's. End up with negative 5, 6. So you could write it as just y-intercept equals negative 5, 6, or you could write it as the point. When x is 0, y is negative 5 over 6. All right. Let's do number 9 here. Find its y-intercept. So it's always let x equal 0, and then solve for y. So plugging in the zeros. And what you're going to find is it's just the constant of the numerator divided by the constant of the denominator. So a negative 24 divided by negative 10. And then you can reduce that down. 2 negatives make a positive, and then 2 will go into both of those. 12/5. So it's the fraction 0, or the point rather, 0 12/5. All right, coming back up here to find the x-intercept, or the zeros of the function. That's another way of looking at it, because we've talked about zeros when we talked about polynomial. You're going to let y equal 0, and then solve. All right, so if I let y equal 0, I'm going to have to do a little bit of algebra here. I've got 0 equals x minus 5 over x plus 6. All right. It's a problem that has a fraction in it. I'm going to clear fractions. Multiply both sides by that denominator so that it cancels out on the right. But 0 times anything is going to result in a 0. And then solve for x. So add 5 to both sides. And our x-intercept then would be at 5, 0. Right. Let's try the next one over here. Find the x-intercept. Let y equal 0. Now you're going to see what's going to happen here, because I'm going to ultimately have to get rid of the denominator. So when I do that, that's my dog panting in the background there. When I do that, you're really just setting the numerator equal to 0. Right? Because 0 times this is always going to be 0. The denominator is always going to cancel out. So you're just setting the numerator equal to 0 when you want to find the x-intercept. Now this time it's a quadratic, so I'm going to have to factor it or use the quadratic formula if I want. And this one's going to happen to have 2 x-intercepts. Set each factor equal to 0, solve for x. So you got x equals 6 or x equals negative 4. So as a point, it would be 6, 0. And then again, the x value is negative 4, 0.